Today we will start a new topic, that programmable logic devices. So, what do we mean by programmable logic devices, and what are the different categories of this device, how the digital designs can be made using these programmable logic devices. We will read all these things in this class. So, first we see what do we mean by a programmable logic device, or in short we call PLD. So, a PLD is an IC chip, we think, that includes arrays of logic elements with user specific connections among these elements. Normally it has two different arrays, and they can be programmed from outside. Now, we will see how these arrays are programmed, what is the structure of this array later, and why it is so popular, or what is the advantage. So, mainly this is the programmable logic part, or PLD consists of the programmable logic part and the large volumes which is most economical to produce an IC. We know that the integrated circuit, that is the advantage, is mainly the when we have discussed the VLSI. So, we want nowadays we want that IC should be made such that large volume of designs can be consists of a or can be fabricated on a silicon. Now, this is the advantage of that programmable logic, that within small area these devices can be fabricated. So, that is why nowadays this is the state of the art of the digital design, that the IC or most of the IC consists of a PLDs. Now, what is the advantages of programmable logics? So, PLD belongs to a larger groups of programmable chips called ASIC. See, we know that ASIC is the application specific integrated circuit, we discussed earlier, and that can include the digital design, that can include the analog or mixed analog and digital circuits. Now, the advantages of this programmable logic over ASIC means, if this is a pure digital, analog or mixed type, where the program PLDs are not there, we have designed that the different type of design we have discussed, that semi custom, full custom, where the PLDs are not there. Now, if we consider the ASIC with PLDs, then the chip count and physical size can be minimized. Why physical size is minimized? Because as already I mentioned, this is very compact, and a large volume of PLDs can contain in a very small area in the IC. Another thing is, as already the arrays are there, see, just very simple way what we can tell, say, as if, say, this is some 2D arrays. Say this is some of the rows, and say some of the columns are there. We will see later that how actually they are designed. Now, whether here there is a connection or not, that means, if I put a transistor here, say here, or that can be in diode, that can be transistors, in this way if we put, then that can be programmed from outside. So, this is the user specification, or depending on the requirement what they want to design, as if these lines can be controlled from outside. So, or this can be controlled means this can be programmed from the outside. So, the main advantage is that here the everything is already there or it is fabricated, only it is programmed from the outside. So, time from design concept to market the system, that means once the problem is identified or what design we want, starting from there, that will to marketing the system, this time can be minimized, because only program time is needed or the hardware is actually available or already pre-designed in the ASIC. Now, programmable logic devices can be used to prototype design that will be implemented for sale in regular ICs. So, if one is available, that means the prototype designs that it is available, then only again depending on the users or the depending on the variety of design requirement that can be programmed. So, this is a very good advantage. Now, some more advantages we see that many programmable logic devices are field programmable, that is can be programmed outside of the manufacturing environment. Most programmable logic devices are erasable and reprogrammable. This is one of the very important issue or the property why the programmable logic devices are so popular or becomes the state of the art of the digital design. See, they can be erasable and reprogrammable. So, one prototype is available, or see that one what we have described, that as if one array of logics are there, this hardware is available. From outside, depending on the design requirement, we are programming that thing. So, we get one specific hardware. Now, as its work or its demand finishes, its requirement finishes, then the same hardware we can use for another design. That is why it can be made erasable and reprogrammable. Now, updating, for these purposes we need the two things. One is how to update and how to reuse. So, updating means allows the device to correct errors. See, even the program is available and say minor modifications are needed, then it can be done. And reusability allows reuse the device for a different design, that is that reprogrammable, or the hardware is there and the different programming we can embed on these on different time. So, we will get a different design on the same hardware, and this is called the reusability of the PLDs. So, this is one of the major property or the design property of PLD, that why it is so important or why it becomes the state of the art of the digital design. Now, what are the disadvantages? There are some minor disadvantages are there, because now the complex PLDs are used, and while the PLD minimizes the chip count of a digital system, the disadvantage is that the interconnections between elements on the chip must be specified or programmed. So, when that interconnections, this is one sense it is a flexibility, but as well as this is very cumbersome to do that thing, because we have the cells to be programmed or the logic cells as well as the interconnections that to be programmed, and this becomes the it makes the system or the design to be complex. Unlike conventional circuits, even after PLD are wired into a system, they will not function properly unless they have been programmed. So, obviously, I have only one fixed hardware, and unless I program it correctly, it should not work. Now, what are the technologies for PLDs? Technologies means that mainly the programming technologies. Now, programming technologies are used to control connections, to build lookup tables and to control transistor switching. Now, one by one we see that thing. First we see the control connections. So, these are normally these mask programming or fuse and anti-fuse that are being used. We see that thing already, say if we see like that, say I have some, okay, there I take it only two things. So, these are some arrays. Now, I want, say here some transistors are there. So, if I give this gate, say if it is a pass transistor, if I give gate a 1, then this and this should be connected. That means which lines? These lines and these lines. That means this point I will be getting on. Then I am calling this is a fuse. That means this. The reverse thing should be that reverse technology is the anti-fuse. So, in that way, that means if I put, we can tell this is a switch. So, if I have a generic or a general array and I whether I want a connection or not, that means here if I get a 1 or 0, then what I will be doing, that I will fuse this connection. That means it can be a transistor, it can be a diode at every cross points. This is a, if this array is a n by n, then there are n square cross points are there, and these cross points whether I get a connection or not, then accordingly the element that has been used, element the either this can be a transistor or this can be a diode, then these elements are on or off, or the proper voltages, this can be programmed, we can tell. So, this is normally just to control circuits, we call that this is fuse, anti-fuse or the mask programming are being used. So, this is for the control connections. Now, another basic building block of the PLDs are the lookup tables. Normally, the PLDs are implemented using the concept of lookup tables, and all lookup tables. So, what is lookup table? We see again, we take an example. Say I have one table. I have one table, okay, and here something is stored, some values are stored. So, here it is stored 1, 5, 6, 9, A, 3, C, like that. Now, so this is in this table some values are stored. Now, if I want to get a value, then I have to give the which location A is stored, and say actually normally this location we call the address of the table or the location. That means whenever I want to get A from this table, I want to get A from this table, I will give a location of A, location of A, and from there I will access A. Similarly, so this is the concept of the lookup table. Now, see, if I treat this table as if these locations are nothing but the address. These locations we can take the addresses of the memory, and the memory content are the table content. So, the memory content normally these are 0 or 1 for 1 bit, that can be, these are actually the table content. So, in this case this lookup table can be used as a memory, because these locations of the table where some value is stored, these locations are treated as the address of the memory, and the content of the table is the content of the memory or memory element, 1 bit or if it is a 8 bit, 32 bit memory, whatever be the thing, that is the content of the table, or this is the memory element. That is why the lookup table can be always that can be implemented as a memory elements. So, lookup tables is nothing but the memory elements. Then transistor switching control. So, this can be erasable, because already we have discussed that the PLDs can be erasable and reprogrammable. So, then we will use that type of switching or transistor switching which is say erasable, means the volatile, electrically erasable or the flash memory. That means, if it is this type of control we use for the transistor switching control. Then normally PLD technologies are either it can be permanent. Permanent means cannot be erased and reprogrammed. That means the memory we will use, if it is a ROM, read only memory type. We have seen that if it is a lookup table based, and lookup table can be implemented by memory, and if this memory is a read only memory type, that means it cannot be changed, then it is a permanent, cannot be erased and reprogrammed. That means, once we have programmed a design, this is a permanent or fixed one. So, though we are calling this is a programmable logic, but actually the programmable means that only the hardware is available and only one time we can program the devices and we will get a one fixed design. Now, reprogrammable. These are of volatile or non-volatiles, means everything volatile means everything goes if power goes. If we use a volatile memory, that means here everything we are using the lookup table is how the lookup table is implemented by what type of memory. So, if we use the memory element or the memory type of memory, so if this is a ROM type, then it is a permanent PLD. We will get only one fixed design for one PLD, permanent type. Now, if it is a RAM type, that means we can change. Here also there can be two type, volatile memory or non-volatile. If it is a volatile, we know that if power goes, then everything will go. If it is non-volatile, that means once we have program, then it will be there. So, depending on the requirement or the board we use, say for academic purposes or for our laboratory uses, if we use some programmable devices, obviously we want that some reprogrammable type of thing. That means once the logic devices are available, programmable logic devices, say we will program for one particular design, and then if it is a volatile, if the power goes, everything will go, or even if the power is there, it can be a non-volatile, that if power goes, then also we will get a same design, but it can be reprogrammed. That means it can be erasable, and so here also for it is a that erasable type of EPROM, that erasable programmable ROM, that also we can use here. So, EPROM also we can use. So, mainly the type of different type of memory we use, depending on that different type of PLDs we can get. Now, we see what are the different configurations. Normally, we call the PLD classes. So, these are programmable read-only memory (PROM), programmable array logic, the PAL, programmable logic array, PLA, complex programmable logic devices we call CPLD, and field programmable gate array FPGA. So, one by one we will see that what do we mean by all these classes, what are the differences, etc. First we see the read-only memory type. So, this is a fixed array of AND gates and a programmable array of OR gates. First thing is, whatever be the type, normally the first three, the programmable read-only memory, programmable array logic and programmable logic array, for these three there are two arrays. The first array is called the AND array and the second array is called the OR array. Now, both arrays can be programmed. Now, depending on the programmability or the order of programmability, degree of programmability, these classifications have been done. So, if it is a fixed AND array and only the OR array can be programmed, then we are calling that this is a read-only memory. So, the structure is if we apply the inputs to the fixed array, fixed AND array and the AND array outputs, these programmable connections, these can be programmed and it is going to a programmable OR array and giving the outputs. Now, programmable array logic, PAL. So, here a programmable array of AND gates feeding a fixed array of OR gates. That means, PAL is just the reverse of PROM, programmable read-only memory. See here, the AND array is programmable. So, when the inputs are going, that can be programmable connections. Array is programmed, array can be programmed, this AND array can be programmed, and this is a fixed OR array. but OR array is fixed. So, this is called the PAL, programmable array logic. And programmable logic array, PLA. Here this is more flexible at the both the arrays, AND array and the OR array, both the arrays can be programmed. See, this is programmable AND array, programmable OR array, and the connections inputs as well as the intermediate inputs of the OR array both can be programmed. So, this is called the PLA. Now, we see that complex programmable logic devices. So, now we have seen that PLD blocks that can be say PROM type, PLA type, PAL type. 3 we have already said: programmable array logic, programmable logic array. Now, using any one of these, we have seen that this is the PLD blocks, programmable logic devices blocks, and there are some IO blocks, and these are these are interconnection matrices. Now, from this interconnection matrix we can communicate, or the switch can be done, switching or the interconnections can be done using the with the PLD blocks. So, these PLD blocks. Similarly, these PLD blocks, the interconnections can be made. So, these are the now there are some IO blocks. So, this is my IO, this is my IO blocks. Say the left hand side, as if we are taking, these are the inputs. So, as if these are my input. So, first the inputs are feeding. So, there must be some interconnection between the IO blocks and the PLDs. Similarly, here, and there the control lines are also coming from the interconnection blocks, IO blocks to interconnection. So, there must be some interconnection between IO block and interconnection matrix, because actually it will control the connection, which PLD blocks will be selected or which will be connected. So, from IO blocks these interconnections are there. Now, the PLD blocks are selected and say some outputs are generated. So, again this side, that with these PLD blocks also the outputs, input output block, here also these two are IO block, that is also there, and there must be the similar type of interconnection between the IO block and the PLD block. Here also the similar interconnections are there, and between the IO block and the interconnection matrix there can be the connection. Another thing is that, see, these IO block, not only as an example I have told that this can be input. Say from this PLD block some of the things can be the output. Some outputs can be taken from this side, or here also some inputs can be applied from this side. So, it is totally programmable and totally flexible, only this is a compact architecture, that some PLD blocks, some IO blocks and interconnection matrix. So, what we can tell that CPLD, so if we take the CPLD blocks, so it has three components. One is that some PLD blocks that can be made by PROM, by PAL, by PLA. Second is the IO block, from the inputs and outputs are fed or taken out. So, this is IO block, and then the interconnection block. So, interconnection block that is between IO and interconnections or interconnection to PLD blocks. So, mainly these three are the three basic blocks that is there in the CPLD structure. Now, another is field programmable gate array, and nowadays this is the state of the art of the VLSI design. So, as I mentioned that these PLD devices are one of the basic building blocks of the ICs now, and as the large volume of design can be built or can be fabricated on a piece of silicon. So, this field programmable gate array is nowadays an alternate to the normal CMOS ASIC. Now, we see the structure. This is similar to the CPLD. We will see that see here also that it is a 2D grid structure. And in the boundary the IO blocks are there. So, these are my IO blocks, input, output blocks, these are and this if we as if we treat this 2D grid and or as a matrix, these matrix elements are of two types. See, in the picture we have shown one small green block. This is our actually these are my logic cells or logic blocks. And this larger yellow one we take, these are my switching block or switch cells, switch cell or switching block. Now, this can be, this is field programmable. So, actually from outside that electrically this can be programmed, these cells can be programmed, as well as these input outputs also can be programmed here. So, this is a totally flexible architecture. So, mainly this is the fixed hardware, or this is just like a form, that as if one hardware form, where the three different type of hardwares, one are the logic cells, switching blocks, and the IO blocks that are available, or we can take IO cell, logic cell, switching cell, all are arranged in a 2D fashion, and they are programmed from the outside. So, this is the overall concept of the FPGA. Later again we will discuss in details. Now, we start that. So, again if I summarize what so far we have read, the different configurations of the PLD. One is the programmable ROM, PROM, programmable array logic, PAL, programmable logic array, PLA, complex programmable logic device, CPLD, and the field programmable gate array, FPGA. Now, we will start discussion in details of the architecture or the actual architecture of the all these PLDs. So, first we see the programmable ROM, the first one. As already I defined, or I have told that this is a read only memories or programmable read only memories. So, if it is a read only memories, it has some in the memory we know that these are some addresses and some output. Address means that we give from which memory element I want to get, and as if output is the nothing but my memory content. So, here the specification is that there are n input lines, m output lines, and 2 to the power n decoded minterms. If it is n input line, so we can by n input line we can represent 2 to the power n values, and this 2 to the power n can be the minterm, as if the n input lines are nothing but the n input variables. So, all these 2 to the power n values will give my that minterms using n input variables, and m output lines. So, m output lines, that means I can get 2 to the power m values again. So, m output lines, so as if my content is a m bit. So, my as if this is a m bit memory. So, as already we defined, the configuration of PROM is a fixed AND array and a programmable OR array. So, if we remember the PROM, see this is the fixed AND array. So, inputs are coming, these inputs are n bit, and this is a fixed OR array. So, fixed AND array with 2 to the power n inputs implementing all n literal minterms, and programmable OR array with m output lines to form up to m sum of minterm expressions. So, if block diagram level if we see, it can be like that. Say I have two array. So, this is my AND array, this is my OR array. Say n input lines I am feeding n inputs. So, as if I am giving these as n variables, these I can represent as if n these are my n variables. So, here actually 2 to the power n min terms can be, these AND can represent 2 to the power n min terms, because n input variable 2 to the power min terms. So, as if these 2 to the power n min terms, output is actually 2 to the power n, and that is fed to my OR array, and this OR array is m output. So, m outputs I can get from this OR array. That means, I can from these 2 to the power n min terms, or using this 2 to the power n min terms, I can form m number of equations. That means, these outputs, if I tell these are my F1, F2, say Fm, then this F1 equal to, from these min terms, some min terms, say M1, M2, like that. So, similarly, Fi is some M1, M2, M5, like it. So, in this way I can form some Fm. So, this is the configuration or the architecture of PROM. So, it has n outputs, it has 2 to the power n inputs of the fixed, this is fixed AND array. So, all 2 to the power n min terms can be treated as the output of the fixed AND array. These are fed to the OR array, and from there according this can be programmed, this OR is programmed. So, actually depending on the design requirement, design specification, which min terms will be selected. See here F1 is M1 plus M2 plus say M7. So, here I will be taken these 3, and accordingly this M1 plus M2 plus M7, that is going to F1. Say Fi, say this is my Fi, and that is nothing but M1 plus M2 plus M5. So, M5 plus M9 plus M9, and that is taken as the. So, these m number of outputs or m outputs can be constructed from 2 to the power n min terms. So, this is the concept of the PROM. Now, if one entry, a connection is made to the corresponding min term for the corresponding output. If a 0, no connection is made. So, this is the conventional things. That means, when I get the AND array, which min term I will be taken, which min term, just now I have shown that M1 plus M2 plus M5. Then the M1 crosses, I will give a 1 entry, just like that our Karnaugh map conventional kernel map does. Can be viewed as a memory with the inputs as addresses of data, hence ROM or PROM names. That why it is called a, this is a programmable logic, why it is called a ROM, read only memory. See, it has some fixed 2 to the power n, just now I have shown. So, if I consider only the OR as if it has 2 to the power n inputs, the min terms, this can be treated as a addresses. So, this is a n bit as if this is n bit address, and from there which value as if these addresses that will give that the values will be taken. So, this is the M1 or that what just now I called F1 are taken. So, this can be address and this output is nothing but the as if the content of memory, which is actually the sum of min terms, selected min terms, sum of min terms selected, and how it is selected, that the as it is programmed. So, these are the sum of selected min terms depending on the program, because it is a programmable OR. This is a OR and that is programmable. This is OR block and this is programmable. So, what actually we are getting, this is nothing but a address is address and the content of memory. So, this is as if read only memory, the ROM. And as the OR is programmable, so this is also programmable ROM. So, programmable PLD, that is a programmable ROM or PROM. Now, we take one example. Say we are taking a 8x4 ROM. So, 8x4 ROM means there are 8 address lines. So, if we see one memory, it has 8 address lines and 4-bit content output. So, what we can do, if I want to get this thing by, or I want to implement this thing by PROM or programmable logic device, then this is my AND, this is my OR. So, here 8 address lines. So, I know 2 to the power 3 equal to 8, 2 to the power 3 equal to 8. So, here AND gate, there will be 3 inputs, 3 input variable. And number of minterms, that there will be 8 minterms that will be fed, and there are 4 bits. So, these are F1, F4. And it can be programmed. So, actually depending on the F1, F2, F3, F4 values, that means my required design or the design requirement, that which minterms will be selected, that will be programmed. So, this part is programmable, this is programmable, which minterm will be selected. So, this is my mapping, that a 8x4 ROM, and that is, this is the programmable thing. Now, this fixed AND array is nothing but a decoder, because it has 3 input, 8 output, that means it is a 3x8 decoder, and 8 outputs implementing minterms. The programmable OR array uses a single line to represent all inputs to an OR gate, and cross in the array corresponds to attaching the minterm to the OR array. That means a cross means it is a 1 there, that means that particular, or we can tell the it is fused, or we can tell the switching element, transistor or diode that is there, that is on, whatever we call, in different level of design specification, and the how the programming is done on the programmable OR. So, we see the design. See, if we draw, so this is my 3x8. So, this is a nothing but a 3x8 decoder. It has 3 inputs. Say A, B, C. So, there are 3 inputs. Now, there are 3x8 decoders. So, 8 output lines, 2, 3, 4, 5, 6, 7, 8. There are 4 output lines. So, this is my, as if this decoder, this is the decoder, this give me the fixed, this give me the fixed AND gate, AND array, fixed AND array, fixed AND array, and this is my programmable OR. This portion is my programmable OR array. So, F3, see here there is a cross point, this is one cross, this is one cross, this is one cross. So, what is my F3? See, my F3 is this min term coming from the D7, that means my A, B, C, say if it is 1 1 1, in that way we take. So, this is A, B, C plus say D5 means 101 means A, B bar C plus the D2 means 0 1 0. So, A bar, B, C bar. So, my F3, the one of the output is ABC plus A bar C plus A bar B C bar. Similarly, F2, we are seeing that these two are the. So, what is my F2? Then my F2 is D0 means A bar, B bar, C bar all 0 plus ABC. My F1 is 0 0 1 means A bar, B bar, C plus 1 0 0 means A, B bar, C bar. My F0 is this cross term plus this min term plus this min term. In this way we can draw this thing. Now, we see today's quiz questions. Say, what is programmable logic device? Name its different configuration as I discussed. What is the difference between PROM and a PAL? What is the difference between a PLA and a PAL? So, mainly the different configurations and what are the differences between the different configurations, that are the main quiz questions of lecture 26. In the last class, we have started the discussion on programmable logic devices. So far, we have read what do we mean by programmable logic devices and the different configurations. Now, we will continue this class the same thing, the programmable logic device. But before that, quickly we see the last class, the quiz questions of the last lecture. So, first question was, what is programmable logic device? Name its different configurations. So, programmable logic devices